Hello friends, I Pankaj Dumka welcomes you all to this discussion on fluid mechanics. Today I will be telling you that how to derive Euler's equation from the control volume approach. In the last lecture, what you have seen is the derivation of Euler's equation from control mass approach. So to proceed this, what we have to do is we have to intuitively find out what can be the momentum equation or momentum conservation when we apply it to a control volume. So this will be the net mass efflux, sorry, as this is momentum equation, so net momentum efflux from the control volume plus the rate of accumulation of the momentum in the control volume, that should be equal to the net force. Okay, now to start with, I would like to tell you that if v is the velocity vector having components u, v and w in x, y and z direction, and x is the body force which is acting on this particular control volume having component xx, xy and xz in x, y, ij, x, y, z direction, then the mass flow in the x direction from any x phase, that is the phase perpendicular to x-axis, if your coordinates are this is x, this is y and this is z, then m dot x will be rho times phase area which is perpendicular to x-axis, that is dy dz. If this is dx, this is dy and this is dz, then times the velocity in that direction. Likewise m dot y, it is rho dx dz v, and m dot z which is rho dx dy w. Now what is the momentum flux which is entering the x phase? That will be m dot times the velocity vector, that means m dot x times the velocity vector. Likewise the momentum flux which is entering the y phase, that will be m dot y v vector, and the z phase, that will be m dot z v vector. Okay, now if you write these fluxes, then you can write this m dot x v in from the x phase as rho dy dz ui plus vj plus wk, from the y phase as rho dx dz ui plus vj plus wk, and from the z phase as rho dx dy ui vj plus wk, which can further be written as, look, rho u, and I have missed one thing, I have missed u here, y component velocity here, and z component velocity here. So it is rho u square dx dy I direction plus rho uv dx dy in the y direction, and rho uw dx dy in the z direction. Likewise here it is rho uv dx dz I plus rho v square dx dz j plus rho vw dx dz k, and for the z phase it is rho w dx dy x phase, x direction, sorry, rho wv dx dy y direction, and rho w square dx dy z direction. Okay, now let me write all the components separately. So in the x direction, from the x phase it is rho u square dx dy. In the y direction from the x phase it is rho uv dx dy, and in the z direction from the x face it is rho uw dx dz. Likewise, from the y face in the x direction it is rho uv dx dz. Y direction y face rho v square dx dz. Y direction y face z direction it is rho vw dx dz. Likewise, z face x direction rho wu dx dy. Z face y direction rho wv dx dy, and z face z direction rho w square dx dy. So these are the components of momentum flux from different faces along different direction. So what I'll be doing is I will be focusing only on the x direction, and rest will be very similar. Okay, so if you look this control volume, then what I can write, this is dy. So the momentum flux which is entering this control volume in x direction from x face, it will be rho u square dx, dy dz, and the one which is exiting the from the x face in the x direction, it is rho u square dy dz plus del by del x rho u square dy dz dx. Okay, now the one which is entering the y face but in the x direction, this is rho u v this is dx dz, and exiting this one from the y face, that in the after a distance dy, it will be rho uv dx dz plus del by del y rho uv dx dz dy. And in the z direction, in the x direction from the z face, it is entering with rho uw dx dy, and exiting with rho uw dx dy plus del by del z rho uw dx dy dz. Okay, so the question is, what is the net momentum flux, efflux basically? What is the net momentum efflux which is leaving the control volume? That will be in the x direction, that will be rho, this in the x direction first look. So let me cancel it one by one. So in the x direction, this will be rho u square dy dz plus this term minus this. So this will be cancelling out. Likewise, in the y direction, it will be rho uv dx dz and this term exiting. So net efflux will be this minus this. So this will be cancelling out. And in the z direction, this will be this term minus this term. Okay, so this will be cancelling out. So you are left with this term here, this term, and this term. So the net momentum efflux, so the net momentum efflux from the control volume in the x direction, that will be from the x face in the x direction first, that is del by del x rho u square dy dz dx plus del by del y rho uv, and then dx dz dy, then del by del z rho uw dx dy and dz. Now you look, this is partial derivative with respect to x, so these will be a constant. this is partial derivative with respect to y, so these will be a constant, and this is partial derivative with respect to z, so these will be a constant, so they can be taken outside, and this expression simply get reduced to rho u square plus del by del y rho uv plus del by del z rho u w, and you are left with dx dy dz, which is nothing but the volume of this control volume. So this is the net momentum efflux from the control volume in the x direction. Now, what is the momentum in the x direction? The momentum in the x direction is what it is, mass times velocity in the x direction. So that is rho dv is the mass of fluid within the control volume at that instant times the velocity. So the rate at which this is accumulated within the control volume, that will be given by this. So this is what? This is the rate of accumulation of momentum within the control volume in x direction. Okay, so the left hand part of the equation which we have intuitively developed is done. Now comes the right hand part, that is the net force. So let me call this as equation 1, this as equation 2. Okay, now the forces. Now if you draw the control volume once again, okay, this is the control volume, okay, and the axis, x-axis, y-axis, z-axis, this is dx, this is dy, and this is dz. So in the x direction, as this is an ideal fluid, so only normal compressive forces will be acting, so it is pressure force only. So it is P times area, that is dy dz, and after a distance of dx, it will be P plus del P by del x dx times area, which is dy dz. Now apart from this surface force, one body force will be there which will be acting in the x direction, that is, let me change the pen, so that is body force, that is this x vector times mass, that I'm sorry, in the x direction it has to be component of that, this times mass, that is rho dv. Okay, so the net force in x direction will be what? That will be rho xx dv plus p dy dz minus p plus del p by del x dx dy dz. Okay, so this is the net force acting on this control volume in the x direction. So this will be cancelling out and you are left with rho xx. Now this is dx dy dz, this is dv, so dv will be taken as a common. So this is equation number 3. Now the net momentum efflux from the control volume in the x direction, this equation 1, plus the rate of accumulation of momentum in the control volume in the x direction, that is equation 2, will be equal to equation number 3. So let me write this. So it is del by del x of rho u square plus del by del y of rho uv plus del by del z of rho uw. This is the net momentum efflux in the x direction from the control volume, plus the rate of accumulation of momentum within the control volume in the x direction, that has to be equal to net force, that is rho xx minus del p by del x dv. Now look, this dv is an arbitrary volume, so this can't be 0, so therefore you can remove this, so you are left with del by del t rho u plus del by del x rho u square plus del by del y rho uv plus del by del z rho uw. Okay, that is equal to rho xx minus del p by del x. So friends, this is the momentum equation, momentum equation or Euler's equation in the x direction. Okay, now you can do the similar thing for y and z direction. So for y direction, this will be del by del t. You can try it yourself. Del by del x rho uv plus del by del y rho v square plus del by del z rho vw. This is rho xy minus del p by del y, and in the z direction it is del by del t rho w plus del by del x rho w. So it is uw plus del by del y rho vw plus del by del z rho ww, that is rho w square, and that is rho xz minus del p by del z. Now these are what? These are the equations or components of the Euler's equation which you have derived in the x, y and z direction. But remember that these all are what? These all are in compact form or conservative form. So whenever you are applying the conservation laws onto a control volume and then deriving the Euler's equation or energy equation or any equation, so the equation which you will be getting is in compact form or conservative form. Okay, now how to convert this equation into the equation which you have developed last time? That was in non-conservative form, and that was for control mass system, and this is derived for control volume system. So you do what? Left hand, right hand side, there is nothing much to solve. Let us do this for x component, rest will be follow similarly. So x component, let us only solve the left hand side. Okay, so let me write it first. That is del by del t rho u plus del by del x rho u square plus del by del y rho uv plus del by del z rho uw. Now if you write this equation in the form which I suggest to you, then you will be able to appreciate it very well. That is how, let me write it as rho v rho w u. Okay, now you know how to differentiate this product. D by dx of AB is what? This is A dB by dx plus dA by dx. So this will be followed. Okay, so if you do this, then you will be getting rho del u by del t plus u del rho by del t plus rho u del u by del x plus u del by del x of rho u plus rho v del u by del y plus u del by del y of rho v plus rho w del u by del z plus u del by del z of rho w. Now you club the things which have density like this, this, this and this on one side and take rho common. You will be getting del u by del t plus u del u by del x plus v del u by del y plus w del u by del z, and from the terms which are remaining you take u as common, that is x component of velocity common. So it is del rho by del t plus del by del x rho u. Now you can see how this form is converting into a form which is nothing but the continuity equation. Okay, so this is what? This is the continuity equation. That is, it is del rho by del t plus divergence of rho v vector, and we know this is 0. Therefore, this term becomes 0 and you are only left with, so the left hand side becomes rho del u by del t plus u del u by del x plus v del u by del y plus w del u by del z, which is nothing but, this is nothing but the substantive derivative of x component of velocity, that is du by dt. So this is LHS, and when you combine it with RHS, that is rho du by dt, and on RH, on right hand side you have this rho xx minus del p by del x. So it is rho xx minus del p by del x. So this is the equation which you have developed last time. And if you go for y direction, then you will be getting dv by dt is equal to rho xy minus del p by del y. For z direction, it will be rho dw by dt rho xz minus del p by del z. No problem. Hence, we have derived the same Euler's equation, that is the relation between density and velocity field for an ideal fluid from the point of view of a control volume, that is from the control volume approach. So friends, this is all in this particular lecture. In the next lecture, I will be trying to solve the Euler's equation along a streamline, and hence the development of Bernoulli's equation. So in this lecture till this point only. If you liked it, then please do like, share and subscribe. Thank you very much. Take care. Bye.